Good morning friends, welcome back. In our previous lecture we are talking about drag polar, which is expressed as a summation of profile drag and induced drag. Right. So the total drag is half rho v square S into CD, which is half rho v square into CD naught plus ACL square. So this can be further expressed as a summation of profile drag as well as induced drag. Okay, CL square. So this term corresponds to profile drag. So half rho v square is CD naught, where CD naught is the profile drag coefficient, and this particular term corresponds to induced drag. And K is the induced drag correction factor, which is equals to 1 by pi E AR, where E is the Ostwald's efficiency and aspect ratio is B square by S. Now, the Ostwald's efficiency here, what does it mean? How it is going to affect the induced drag? So, what are the boundaries of this Ostwald's efficiency? In our previous lecture, we witnessed the lift distribution along the span of this wing, right? So, for a rectangular wing, let us say this is your planform geometry. Okay. So you are looking, this is your V infinity, this is the top view, right? So how the lift distribution along this span? This is your top view and this is your front view from the front side of the wing, right? So it's like you're facing the aircraft from the nose. Right. Now, if you look at the wing, typically for a rectangular wing, this is how lift distribution. Ideally, this is how it has to be, right? Because at each and every span-wise location, you have an aerofoil which gives you a resultant aerodynamic force, and the component of that you will get as a lift, right? Will contributes towards lift. So typically this is how you have, the lift distribution is for a rectangular wing. Now let us say instead of this rectangular wing, you consider a elliptic wing. It is observed that the lift distribution depends upon the shape of the wing. Right? So for an elliptic wing, you will end up having elliptic lift distribution. Right? For such lift distribution, which is elliptic, the Ostwald's efficiency factor is equals to 1. And the corresponding induced drag will reduce. So the upper limit of this Ostwald's efficiency is 1. That is for elliptic wing. For any other shape, this Ostwald's efficiency factor talks about how good is your lift, or it compares with that of an elliptic wing lift distribution. Let us say if you have designed a wing which is non-elliptic, so this efficiency factor is a kind of figure of merit, and that compares your current wing lift distribution with that of a elliptic wing lift distribution. So for any other geometry, it is more or less than 1. So instead of a rectangular wing, now let us consider an elliptic wing. So this is your rectangular. So how you got this lift distribution? At each and every location, span-wise location, you have an aerofoil with the respective pressure distribution, right? Now, how about the pressure distribution at each and every span-wise location of this elliptic wing? Consider an enlarged view of that elliptic wing, right? Let us say the flow is along this, parallel to this fuselage reference line. So at each and every location, so the white lines here, or the arrows here represents the pressure distribution at each and every location of this elliptic wing, right? Now this pressure distribution is perpendicular to this planform that is coming out of this, perpendicular to this surface of this blackboard. Right? Assume that it is perpendicular to this, and now we can get a resultant force, and a component of that perpendicular to this free stream is the lift at that particular span location, right? At a particular span location, that is your lift, right? Now, say if you get the locus of this lift distribution at each and every span-wise location, then typically this is how it looks like. Say either you are looking from this direction or this direction, right? This is the lift at a particular span-wise location, right? Now, for an elliptic wing, it looks like an elliptic lift distribution, right? So, for a rectangular wing, it looks like a rectangular lift distribution, right? So, what do you infer from here? The planform geometry plays a key role in deciding the lift distribution over the span, right? According to lifting line theory, the wing can be replaced by a bound vertex, and the associated flow field can be replaced by a trailing vertex, two trailing vertex, and this vertex architecture is closed by a starting vertex. So this entire vertex architecture is known as horseshoe vertex, right? So this bound vertex will create an upwash ahead of the wing and downwash behind the wing. So this is by bound vertex. Whereas the trailing vertex will create a downwash throughout the span of the wing, right? This combined effect, like upwash and downwash, will alter the local angle of attack at a particular span-wise location, right? So we have derived it yesterday. This, see, this is your reference line, FRL, fuselage reference line. Let us consider a span-wise location here. So you have an airfoil at this particular location, right? So let's say this is your airfoil at that particular span-wise location. And which is at an angle alpha with respect to free stream velocity of the entire wing, right? But due to this upwash and downwash effect, the local angle of attack at this particular span location changes, right? So this is induced by a downwash, right? This change in angle of attack is because of the downwash. So this is your actual V infinity, this is V infinity at that particular location, V infinity prime, Okay, so the effective angle of attack for this aerofoil is alpha effective EF, or the local angle of attack here is alpha L. So this alpha L is equals to alpha minus alpha I. Now the total lift of the entire wing is perpendicular to the free stream velocity L, but this is the local velocity because of this induced angle of attack alpha I, right? So the local lift will be perpendicular to this particular quantity, right? This is your local lift. Say this is the direction of your drag. This local lift will also have a component along the drag of this entire wing. So, and the component is equals to, say, CDI is equals to CL into this angle is your alpha I, right? CL into sine alpha I. Why? Because this angle is 90 degrees. So these two are perpendicular, V infinity and capital L are perpendicular, and this local lift and this alpha I or V infinity prime is perpendicular, right? So what is this angle? What is this angle? This is 90 minus alpha I. What is this angle? This is 90 minus alpha I. Since this is alpha I, right? This is 90 minus alpha I, and you have this as 90, you have this as 90 minus alpha I, so 90 minus of 90 minus alpha is alpha, right? So L local lift into cos of alpha I is along the total lift direction, and local lift into sine of alpha I will be along the drag direction, total drag of the wing. Now since alpha I is small, we can assume CDI is equals to alpha I. So CDI is equals to, and again we know from the lifting line theory, alpha I is equals to CL by pi E R. So CDI is equals to CL square by pi E AR. So induced drag coefficient is equals to CL square divided by pi E AR. Now this factor E is the Ostwald's efficiency, and from this theory it is observed that for elliptic wing we have minimum induced drag with Ostwald's efficiency factor is equals to 1. So this is the upper limit of this Ostwald's efficiency factor, right? For any other planform, E will be less than 1. In general, you can say E is always less than or equal to 1. So will the lift of the aerofoil and the lift of the wing is made up of aerofoils, a series of aerofoils, right? Will it be same or not? Let us look at, if not, what is the relation between lift of the aerofoil and lift of the wing. No, let us now define what is called zero lift line, right? Say I have an aircraft, I say this is my zero lift line, right? What does it mean? If the flow is along this zero lift line, then there is no lift produced by this aircraft, right? Understood? Now let us define angle of attack with respect to this zero lift line. Say if the flow is in this direction, so this is my alpha of zero lift line, right? So this is my V infinity, alpha with respect to zero lift line. Now how to relate the angle of attack with respect to chord and angle of attack with respect to zero lift line, right? Alpha of zero lift line is equals to alpha minus alpha at CL is equals to 0, Now let's make a wing out of this aerofoil and see how the lifting characteristics of aerofoil are related to a wing. Right. So let us consider a typical lift coefficient variation with angle of attack. Right. Now let us assume this angle of attack is defined with zero lift line, right, where alpha zero lift line is equals to alpha with respect to chord or fuselage reference line minus alpha at CL is equals to CL, right. Let us assume, right. Now what is this y minus here, because like we are actually shifting the axis, y axis here. For example, if this is my CL and alpha with respect to chord line, right. Now with respect to zero lift line, what happens is my alpha zero lift line starts when will be 0 when CL is equals to 0, right. So this is again the same axis, y axis CL, right. So for example, with respect to chord, this is your, so for the same CL, okay, if you are measuring the angle of attack with respect to chord, you express CL is equals to CL naught plus CL alpha into alpha. This is the normal representation of lift where you have zero lift at zero angle of attack, right. Alpha is equals to 0 and y is equals to mx plus c. That is how you are going to express this. And you can also express the CL with the help of zero lift line, right. Where I mean you can express, see we are trying to find out the same CL with when we define the angle of attack with respect to zero lift line, right. So zero lift line is like when the V infinity is along that zero lift line or along the reference line, then there is no lift produced by this aircraft. So that means you are actually shifting this alpha. See here, when alpha is equals to 0, there is certain lift, but in this case when alpha is equals to 0, there should not be any lift. Lift should also be 0. So according to this, so what you have is CL alpha. See, the slope still remains the same, only the definition of alpha changes here. 0 lift line. Okay. The slope still remains the same here. Okay. Now consider a case where we are defining this lift with respect to zero lift line. Right. Now say typically this is how the aerofoil CL variation with this angle of attack, right, which was defined with respect to zero lift line. That is. Now we know this is your alpha stall where you can achieve your maximum CL max, right. So beyond this what happens? So this is your angle of attack and this is your free stream, this is your alpha. Say at alpha stall, what happens is the flow separates. Flow separation happens over this aerofoil. Major part of the flow will get separated from this aerofoil, because of which there is a sudden drop in CL beyond this alpha stall, right? And the drag also increases because of the, so flow, because of the flow separation you will get pressure drag, right? So now coming back to this, now let us say this is your A naught or CL alpha 2D, which is say CL alpha 2D because it's for aerofoil. I say CL alpha 2D is for aerofoil. So this is for an infinite wing. Now if I make a wing out of it with a finite aspect ratio, this is how typically it will be. So aspect ratio is equals to, say, aspect ratio 2, aspect ratio 1. So this is the increasing order of aspect ratio. Okay. Now, what's happening? The slope is changing. Right here you can see there is a steeper slope, right, and lesser steeper compared to that of airfoil. Now consider, let this be CL alpha 3D, right, for aspect ratio 1, AR2, for AR2, sorry. Okay, with a finite aspect ratio. Now look at CL for 2D case. Let this angular of attack be alpha, right, for this particular case. For the wing made out of the same airfoil, the same CL is achieved at a higher alpha, right. So this is alpha for airfoil, say alpha naught, and this is your alpha, right. This is the alpha for wing, this is for alpha naught for airfoil, at which you are attaining the same CL. Okay. Now this is your induced angle of attack alpha I. The change is because of this induced angle of attack. Okay. So now the CL of this aerofoil at this particular alpha, I can express it as slope of this CL2D into the corresponding y is equal to mx. Since we have defined this angle of attack with respect to zero lift line here. So CL alpha 2D into alpha naught. So this alpha naught, okay. Now the same CL, if you want to find out from the wing, right, this equals to CL alpha 3D or the wing with finite aspect ratio, right, into this is your alpha. So this is equals to CL alpha 3D is equals to alpha naught plus alpha I. So equating this equation 1 and 2, because both are representing same value of CL. Right? So CL2D, CL alpha 2D. Here it is CL alpha 2D. Please make a correction. So CL alpha 2D CL alpha 2D is equals to CL alpha 2D into alpha naught is equals to CL alpha or CL alpha 3D into alpha, that is equals to CL alpha. So the capital L represents for 3D case, small l represents for 2D case. So I am not explicitly writing 2D and 3D from now. So I am dropping this subscripts here. CL alpha into alpha naught plus alpha I. Alpha I is CL. Alpha I is CL divided by pi E AR. Express it as CL naught, or CL alpha into alpha naught of the aerofoil, right, divided by pi E AR. The same CL can be achieved from the aerofoil as well as the wing. The change is the angle of attack at which you are achieving this CL. Right. For an aerofoil, you can achieve it at alpha naught. This is your alpha naught. This is your alpha at alpha. So this is the induced angle of attack. Right. This induced angle of attack is changing the slope of this 3D and 2D. So this CL I can achieve it from the airfoil as well, from CL alpha into alpha naught. right? If I substitute this in that equation, so CL alpha into alpha naught is equals to CL alpha of wing into alpha naught plus CL alpha into alpha naught of wing of airfoil, sorry, divided by pi e air. This implies CL alpha is equals to CL alpha of airfoil divided by 1 plus CL alpha of airfoil by E air. Now this is one of the important result. So this is well valid in the subsonic regimes, right? So the 3D wing CL alpha, which is made out of the aerofoils with CL alpha 2D, right, is related by this equation. CL alpha by 1 plus CL alpha by pi E air. So if I have an elliptic wing, then E becomes 1. So this is clear, right? So the same CL can be achieved from the aerofoil and the wing made out of these aerofoils, right? So as the aspect ratio changes, the CL alpha curve changes, right? Let us say for the 2D case, it is the maximum, right? Let this point be the CL, and the corresponding angle of attack at which it is achieved is alpha naught, right? And CL alpha represents the 2D case, which is the aerofoil CL alpha, right? And now you have a wing with a finite aspect ratio, and the same CL is achieved at an angle of attack alpha, which is higher than alpha naught, which is in fact the summation of alpha naught plus alpha I. So this additional angle of attack is because of the induced angle of attack, right? Now by assuming a linear equation here, right, y CL is equals to CL alpha of 3D wing into alpha, right? And the same can be achieved by an aerofoil, the same CL, right, at a lesser angle of attack, say alpha naught. Now equating these two, you get CL alpha is equals to CL alpha 2D by 1 plus CL alpha 2D by pi a air. Again 2D and 3D to complete this equation. And now let us look at some of the examples where you have the 2D data, that is airfoil data, and you have a plan form, and you need to find the corresponding CL alpha of 3D wing, right? Consider the following plan form of a fixed wing crop delta UAV aerodynamic center of the configuration. So let the root chord of this UAV be 0.9 meters, and the tip chord is 0.15 meters, and the span is 1.5 meters. Right? So the planform geometry of this fixed wing crop delta UAV is given with the root chord of 0.9 meters and tip chord of 0.15 meters and the span of 1.5 meters. You need to find the aerodynamic center of this configuration. So aerodynamic center XAC is equals to, we derived it, right? Say this is your XAC. So XAC is equals to CR minus 0.75 C bar. Right? So what is XAC? CR minus 0.75 C bar. So I need to know what is C bar here. So this is your, say this is your mean aerodynamic chord, right? Project this mean aerodynamic chord onto the root chord and take 25% of this mean aerodynamic chord, so that you will get the corresponding distance, which is CR minus C plus 0.25 C bar, which is C bar minus CR minus 0.75 C bar. Now to find out C bar, you need 2/3 root chord into 1 plus lambda square divided by 1 plus lambda. So what is lambda? It's CT by CR, which is 0.15 divided by 0.9, which is 0.167, 167, right? Now substitute this lambda in the above equation. 1 plus 0.167 plus 0.167 whole square divided by 1 plus 0.167. So this equals to 0.614 meters. Right? So the mean aerodynamic chord is approximately 0.614 meters. Now, so if you are interested, you can also find what is the y location of this C bar, y location of MAC. So let's quickly do it. Y of C bar is equals to B by 6, 1 plus 2 lambda by 1 plus lambda is equals to 1.5 divided by 6 into 1 plus 2 times of 0.167 divided by 1 plus 0.167. Zero 0.2857 meters approximately. It lies at approximately 29 centimeters from the root chord. What is our mean aerodynamic chord, MAC? Location of this mean aerodynamic center, XAC, is equals to CR minus 0.75 C bar, which is 0.9 minus 0.75 into 0.614. This equals to approximately 0.43 meters. 0.4395 meters, which is approximately 44 centimeters. It is at a location of 44 centimeters from the nose leading edge of this root chord, right? Now let us also find the aspect ratio of this configuration. What is this? What is the aspect ratio? Which it is B square by S, that is 1.5 meter square divided by what is S for this configuration? S is B into the total area of this configuration is B into CR plus CT by 2. This equals to B by 2 into, if I take CR out, this is 1 plus CT by CR, which is lambda. B by 2 into CR into 1 plus lambda. So the area of this configuration is approximately 0.787. So S of this configuration is 0.787 meters square. The aspect ratio is 2.85. So estimate the aerodynamic center of the following UAV, right? Let us assume this is the planform geometry. Now, see here, it's not a single taper, right? It has multiple sections. See, up to here it's a rectangular wing, right? After that is a tapered wing. as a crop delta V, and this taper is about trailing edge here, right? Now what we need to do is, let's divide sections 1 and 2, right? Now let this be 0.9 meters and 0.15. Right. So that means the root chord and tip chord are same as previous example. So the span of this UAV be 2 meters. Right, and say the rectangular portion is 0.5 meters. Now say what will be this portion? This portion will be 0.25, the rest will be 0.75, right? One and two. Now how to find the aerodynamic center for this configuration? Now let us take section 1. What is the area of this section 1? Say S1 is CR into this span, right? So this S1, okay. So let it be small S1, which corresponds to only this particular half. Right, the area that we are going to talk is corresponds to only this particular half. Okay, so S1 here is 0.25 times 0.9, 0.225 meter square. And B1 here is 0.25. And what is CR1 is 0.9, right? What is CT? Since it's a rectangular wing, right? CR1, this section is rectangular, so CR1 is equals to CT1 here, right? So lambda of this particular section is equals to 1, and C bar is simply C bar of first section is 0.9. Right. What about C bar of second section? Section 2. So S2 is equals to 0.75 into 0.9 plus 0.15 divided by 2. This is equals to 0.3938 meters square, right? And B2 is 0.75. And what is CR1? CR2 is equals to 0.9 meters here, which is CT1, right? 0.9 meters. And CT is 0.15. So lambda 2 is equals to CT by CR, which is 0.167. So we did it from, it's the same as previous example, right? So the semi-span of previous example is also 0.5, 0.75, and we have root chord 0.9 and tip chord as 0.15. Oh, what will be the total area? It's S1 plus S2, right? Total area of this half. or say S represents the half area of this wing, right? This equals to S1 plus S2, which is 0.225 plus 0.3938, which is equals to 0.6188 meter square. Now what is C bar for this configuration? C bar for this section 2? C bar is equals to 2/3 CR into 1 plus lambda square divided by 1 plus lambda, which is equals to 0.614 meters. Right? So all dimensions are in meters here. All the lengths are in meters. Now we have C1, C bar 1 and C bar 2. To find out mean aerodynamic chord of this configuration, we can take the weighted average of this, which is C1 bar 1 S1 plus C2 bar into S2 divided by S or S. So this equals to 0.9 into 0.225 plus 0.3938 into 0.614 divided by 0.6188. This equals to 0.718 meters. 0.718. This is a mean aerodynamic chord for this configuration. Now what will be the aspect ratio of this configuration? So aspect ratio can also be obtained by this weighted average, right? So that is, so from the definition, if you remember, it's B square by S, which talks about both the sides, right? Although it is symmetric, it talks about, aspect ratio talks about the entire planform. Now, since you're considering semi-span and semi-area here, so the effective aspect ratio for this multiple sections is twice sigma I is equals to 1 to n. Say n is the number of sections. You can have one more section here, right? Effectively, you can have another section like this. You can have another section like that, right? So sigma I is equals to 1 to n ARI into SI divided by S. So then it becomes, this may be 1, this may be 2, this may be 3. And again you can have a planform, say this may be 4. Right? So you can have n number of sections. Right? There are different tappers at each and every stage. Right? So for this configuration, say 1 and 2, what you have here is 2 times of first aspect ratio of first portion is around 0.2778 into 0.225 plus 0.3938 into 1.4284 otherwise divided by S1 plus S2, which is 0.6188. This equals to 2.02 is the aspect ratio of this planform. Say if you have an elliptic planform like this, right? So you will not be able to find what is the tip chord here. In that case, what you can do is, you can project this taper, you can extend this taper and consider this distance as your tip chord, CT. Right? For an elliptic wing, so here the taper ends, right? After that you will get an ellipse here. So the tip chord can be, you extend this taper of this adjacent section and find the corresponding length here at the tip. Right. So this taper, this chord length will be the tip chord length for the elliptic wing. Dear friends, to my right is a medium altitude surveillance UAV. So it has a pusher configuration. It's a three blade pusher configuration with a T-tail, and there is a twin boom. This T-tail is mounted on a twin boom. So let us look at the planform geometry of this wing. At least one, so this first portion which was in yellow color is a rectangular wing. If you can notice this, the chord is around 0.3 meters. So till this point it is rectangular wing. Beyond this there is a taper up to this point, and beyond this point there is a elliptic planform, right. So to find this mean the mean aerodynamic chord of this planform geometry, we need to adapt the methodology that we have discussed in example 2, right. So from this point, if you want to find the taper ratio of this section, let us say, what you need to do, you need to consider this as your tip chord, right. This as your tip chord. Yeah, consider this portion as your tip chord, and you can find out the corresponding. So it is like you have to find the mean aerodynamic chord by considering this as 3 sections, right. So first with a rectangular section, and then a tapered, and then a elliptic planform.